Okay, so in the triangle-like graph of f below, what is the value needed for f of 0 so that the area under f between f and the x-axis is exactly equal to 1? What height of this triangle makes the area equal to 1? You guys said, 57 people said 0.5. Let's see, what else did people say? Some people said 2, but very common answer was 0.5, and that's the correct answer. So you guys can do geometry. This kind of really basic geometry with triangles and rectangles and stuff is going to be needed to calculate probabilities. Why is that? Well, as soon as you start dealing with uncountable infinities, how do you calculate probabilities? You turn them into areas and you calculate areas. So this is actually setting us up to do some probabilities. And we're going to learn something called the probability density function. That's coming up next. So let's see what that looks like on the doc cam here.
Okay, I'm going to start. I'm going to stick on paper today, and very nice. So just a sec. Let me get the doc cam sitting where it's supposed to be. So we've discussed the probability density function a little bit. It's associated with a continuous random variable. And in a sense, it's analogous to the probability mass function with some significant differences, substantial differences, okay? So in the sense we think of it kind of analogous to the probability mass function, which of course is for discrete random variables. For continuous random variables, we have this function we call the probability density function, but there are certain characteristics about it we want to make sure we understand. And well, you know what I'm going to do is I'm going to start off with a very basic definition of a probability density function. I'm going to do this on everything on paper today. So we'll call this defining a probability density function, which we call the PDF. As opposed to the file format, PDF file format, which is a different PDF, but we could have a PDF about the probability density function, so we'd have a PDF of a PDF, something like that. Okay, so the following definition, I decided, I could give a various definition, but I want to give you the one that you are likely to see when you go to your third year course in Mass Stats. Okay, when you take Mass Stats 1 in your third year, the usual textbook they use for there is one by Freund and Walpole. So I'm going to put this as a Freund and Walpole definition. And this is word by word, exactly what they put here, and that is a function with values f of x defined over the set of all real numbers is called a probability density function of the continuous random variable x if and only if the probability that A is between x and b is, well, we're going to have to explain this because most haven't had integral calculus right now, but this is the definition. What we're going to do is say, hey, this actually isn't that hard of a definition. So this is an integral sign, and so this is saying we integrate f of x dx and evaluate that between b and a. It's going to give us something. For any real constants, a and b, with a less than or equal to b. Okay, so that's a mathematical definition. As I say, this is the one in the math stats book that is typically used in the third year. So let's unpack what that definition is telling us. Looks funky. Looks very funky. Okay. First of all, a couple of notes. F of x has to be greater than or equal to 0. For all x. If you integrate from negative infinity to infinity of f of x dx, that has to be equal to 1. So, what does this represent? What's this idea f of x dx between a and b? Well, we've worked with a uniform distribution, but we could work with some other kind of distribution. It doesn't matter what it is. And here's just a generic distribution of some type. I'm going to just draw a generic probability density function, and I'm going to freeze this on one side. And so if I've got some function, why don't we work out the one that we just worked with? We just had this one. So this is the x, and off in that direction it's heading off to positive infinity, and in this direction it's heading off to negative infinity. And this is just the real line. And what you did was you said, hey, what's this value, f of 0, such that the area under this spot from negative 2 to 2 was equal to 1. And what you found here was that your f of 0 was equal to, no, it wasn't 1, it was 1/2, right? 1/2. So that value f of 0 at 1/2 meant that you had a total area under this curve of 1, and this is the axis for f of x. Now, going back to our definition, what does this say? The probability that x falls between a and b, where a is less than or equal to b, is this integral. What that's telling us is it's just an area under the curve. Okay, so f of x dx from A to B, yes, we have said it's the probability A is less than or equal to X is less than or equal to B, and that translates to the area under the curve between points A and B. Okay, so we can use calculus to find this for fancy shaped curves. We're going to have another way of, we can use R to get areas under the curve for some challenging but important distributions. We'll see one of those, but some of these questions can be done easily with geometric arguments, okay? So basically you need to know how to get the area of a rectangle, and you need to know how to get the area of a triangle. And those aren't too bad, right? So everything that we give you on geometric arguments is going to break down to, can you get the area of a rectangle, can you get the area of a triangle? So let's just ask ourselves one here, for example. Okay, how am I going to do something like this? So let's do an example for this one. For the above PDF. And you know what I've left unstated here? Left unstated on this is this particular value where this is sitting here is 0 heading off to positive infinity. Okay, so this x-axis is occurring at where we're drawing our x-axis through is at y equals 0. Okay. So let's just see. Example for this. Find the probability that, let's make it a somewhat challenging one, not all that challenging. Let's suppose we want the probability that x is between, let's take 1/2 and 1. And so for a geometric argument, we can look at this thing and say, okay, let's see, this is where 1 sits, and here's where 1/2 sits, and what we want to do is find this area right here. And we're not going to make this one a mathematized exercise, but let's just work that out and take a consensus of what we end up with there.
Tricky.
It's a little tricky.
Yeah. You gotta know your lines.
Conspicuous consensus? Got an answer for that one? No, got an answer? Got an answer? Got an answer? Got an answer? No? So tells me he thinks I've asked a tricky question. How many thinks I've asked a tricky question? How many feel they've got the answer? Everybody feel they got the answer? Okay. We're going to answer this one this way. Let me leave you that question. Mathematize exercise next class, and that'll give you something to start off with. So we're going to leave that one as people are finding this one hard, as you kind of suspect, a little tricky. So we're going to start this one off as a mathematize question.
Right now?
Next class.
Oh, next class. Okay.
Next class. We'll do that one next class. Okay.
Let's do the probability from 1 to 2. That's the next one.
Let's do 1 to 2.
Let's
Okay.
do 1 to 2.
Okay.
Same deal, but easier.
Did I freeze that? Did I unfreeze it? Oh, I want to unfreeze it on this side. Okay. Little easier question here. Find the probability that x is between 1 and 2.
This one? Let's do it right now.
You can do that right now?
Yeah, we can do that.
You can do that fast.
Yeah, no problem.
You are amazing.
Let's see. Okay, it's live on Mathematize. You guys give us what you got. What's the probability x is between 1 and 2 for this little triangle dealio over here? Oh no, I've written 1 less than x less than 2. You already wrote 1 less than or equal to x less than or equal to 2. Is that different or the same? You guys think about it. Let's pretend it says less than or equal to. Okay, either way, give us what you got. Okay, who would benefit from a little bit more time? One or two people. Let me do like 30 more seconds, and then we'll see where you are. Remember, you can always put in 111 if you don't know. That's a good sign to us to slow down and do it a little bit more carefully. But we do want to see if you can do it. So if you can do it, give it a try, and we'll see. Okay, 5 seconds left. Put in your guesses. Put in 111 if you're really stuck. And let's see what people thought. Okay. What did people think? Let's reveal the counts. All right. Okay. 8 people said 111. That's very good. Some people got a quarter. Some people got a half. Remember, they're probabilities, so it can't be higher than 1. This person probably meant to say 111. Okay. One. I like this one. Very, very classy. And 34 people said an 8. So that's just about half the people. That is the right answer. So half the people got it right. If you got a quarter, you maybe made a silly, you like forgot to divide by 2 in the triangle formula. That's possible. Let's take it up. Gary, why don't you show us?
Let's make a comment about 2.5 and 3.75.
Ooh, yeah, tell us. Oh, yeah, can
probabilities. Can we have probabilities greater than 1? Ooh, that we better just say no. No. Now maybe you're thinking percentage-wise or something like that, but
well, again,
so probability.
If you calculate the area, an area can be 2.5, but the total area is 1. So if you get to calculate a piece of it, remember our first mathematize was this one, and we made sure that the total area was 1. So the total area is 1. So if you take any piece of this triangle, it better have an area less than 1, because the total area is 1. And that's how areas work. So, okay, there we go. So why don't you show us why it's 1/8 for the 50% of people who didn't get it?
Yeah. So, a couple ways you could have gone about this. Simple thing is that 0 to 1, 1 to 2. If you think about dividing this up, to me the simple solution is to think of, okay, do the rectangle in there, and this one here, 0 to 1, 1 to 2. This rectangle is just double that, so I could divide that into 2 areas which are the same as that, and then this one up here will have the same area as this one down here. So yes, this is 1/4 of this half of the area, but we have the other half over here. So yes, it's 1/4 of this half, but that's going to be 1/8. Okay, so again, just try to think of simple geometric arguments. So just kind of setting you up on this one, just kind of think about what you can do with this area between a half and 1, and you might want to consider something like getting the area of this triangle and then figuring out how to subtract the area of that triangle. We will leave that with you. So a couple things that came up on that is, one was this idea. Mihai went and wrote his mathematize, and he didn't give me the less than or equal to signs that I asked for. He just put less than signs in. And the question is, does it matter? Does that matter? Is that different? The answer is simply no. And it's because the equality is looking at a single point on the real line, and the probability associated with any point on the real line is 0. Okay? So from an area perspective, continuous random variables, we interpret probabilities on intervals, and that is an area. area for a single point on the real line is 0. So whether I put less than or equal to or less than doesn't make a difference at all. And in fact, we will tell you that we often flip them around just so, not to confuse you, but to get you used to the idea that it doesn't matter which we put for continuous random variables. Does it make a difference for discrete random variables? Absolutely. You've got to pay attention to a less than versus a less than or equal to for a discrete random variable, not for continuous random variables. So a couple other things we could emphasize here is that got to keep my time here. The area under the curve had to be equal to 1. We could have also asked a question like this. Find the probability that 1 was less than or equal to x is less than or equal to 4, for example. And what would be your answer for that? Anybody got a quick answer for that? Anybody want to give me a quick answer for that one? Again, look at your graph and say, what do you think? What do you think? It's gonna, pardon? Doesn't exist. There's no probability that x can be between 1 and 4, eh? Okay, you got a different attitude or a different answer? Maybe you have a different attitude too.
I think it's 1 over 8 still.
It's still 1 over 8, yeah. So it's 1 over 8, and again, I threw in a value of x, which you're saying, well, you know, it can't be up that high based on that density function. But, you know, 4 is up here, and I've simply said, what's the probability it's between 1 and 4? And yes, between 2 and 4, there's nothing there. And so I could have decomposed that and says that's the probability that x is between 1 and 2, which occurs with non-zero probability, plus, you know, the probability that x is between 2 and 4, which does not occur with non-zero probability, it occurs with 0 probability. So yes, that was going to be 1/8 plus 0 is 1/8. And I typically wouldn't bother writing that in the plus 0. I just recognize the problem collapses down to the probability that x is between 1 and 2. So those kind of things can be thrown in to make life more interesting for you. Okay, next question. I want to peel off more paper. More paper. Okay. So we're on to things. And I'm going to draw a little sketch here. And I'm going to tell you that this area, the length of this here is 0.2. And this is f of x. And this is 0. And this is some value b, which, oh crap, I don't remember what it is. Oh, disaster. Oh, but you people will solve it for me. Okay. A random variable x as the PDF shown above. What is the probability x is greater than 1? I don't know. Did you want to make that mathematized too?
Okay, yeah, sure.
We could. Let's just see what people come up with.
So here, let's freeze.
We'll give it. We'll let people attack it for a bit, and then depending on how they're going on that one, maybe we'll give another hint.
Yeah. Okay. now I gotta do the problem.
Now you gotta do the problem. I'm just gonna check on how a few people are doing so I can determine whether to move ahead with the hand. How we do it. You think you got it? You think you got it? You think you got it? Think you got it? Working it out?
Here, you want to just check my work here? Oh no, wait. Okay, hold on. This is 1 minus. Okay. All right. Very good. All right. Okay. Okay, it's live. You can put in what you think the value of b is, and then you can put in what you think the probability that x is bigger than 1 is. And we're talking about this picture over here.
So Mihai is giving you a hint with what he's looking for, because the very first thing, which I can tell you, many people forget this on a test, the very first thing you've got to do is solve for b, right? And so people often are trying to put answers in terms of b, but no, you can solve for b.
How long, you want to give them 2 minutes or something, or 1 minute?
One more minute.
Let's do 1 more. Okay, let's do 1 more minute, and then we'll see how far you got. If you can figure out one of them, put that one in, and then put in 1, 1, 1 for the other one. So maybe you can do both.
You guess. No, you don't want to guess. Use rigorous logic. No? So that says if your base is 110, its height must be 110.
Does that line continue or does it
No, it stops at b.
Okay.
Properties of congruent triangles are listed.
Right. Well, I did it by finding the value of the one. So I did the sort of no thinking way.
Okay.
Okay, let's put in your guesses. Maybe you know what b is, but not the probability. And we'll, if that's the case, we'll show you maybe some like bread and butter ways to get this area that gives you the probability x equals greater than 1. And yeah, like Gary was saying, you can either be like tricky and do congruent triangles and stuff, or you can be like very like hands-on and just like I'm gonna calculate the height of everything. And that either way will work. All right, let's see what people said. Reveal. Let's see what people said. All right. For B, 38 people said 10. 14 people don't know, which is good to know. Some people said 1, 2, 5, 11. 0.2. If you said 0.2, you're mixing up B, which is the width of the triangle, with 0.2, which is the height of the triangle. Okay, so this triangle, there's something special about it. And, okay, so what is B? It is, in fact, 10, so about half the people got that. So that's good. We'll tell you why it's 10 in a second. But the main reason is that 10 makes it so that the triangle has total area 1. Remember, we always want to have total area 1, just like this thing over here. The total area has to be 1, because otherwise, there's no way in hell that it corresponds to a probability distribution, right? So if it's going to be the probability distribution function for some variable, the area underneath in total better be 1, And then you can figure out probabilities by cutting off little pieces of it. The total area has always got to be 1. Okay, let's go back and see what you said. And then in this one, what did people say? Reveal counts. So 10, and most people are confused here. Great, so let's do this one. This one, you got to know a little bit of geometry and stuff. So maybe that's what you guys are resting on. You got to know how to calculate the heights of things and the areas of things. I will say the most common answer was correct. So congratulations to people who knew that was 0.99. This triangle is the origin of the expression I'm 99% sure. Is this triangle. Okay, I like this. 4 ones. This is good. Good way to let me know. Okay, let's do this one. Let's do this. So
you get any 99 over 100s there?
I got
saw some further down. What was further down?
there's 9 over 10. It's not
9 over
right.
10, 9 over 10,
0.96.
18 over 20.
9.99.
Not a good probability.
This person was so close they just forgot the dot. I feel bad. Okay. All right. Okay, let's do this one. Let's do it. Let's do like hands-on bread and butter calculations. This is like you're in grade school and you must calculate the areas of things. Would you like to do some areas, Gary? Or
Areas.
should I?
You want to do the area?
Sure, I'll do it because I'll do it. Gary has a tricky way to do it with congruent triangles and stuff, but I'm going to just be very hands-on and just calculate the height of this little mini triangle, okay? So this is what we want. We want the 1 over here. But before that, let's figure out what B is. So B must be chosen. Must be chosen. So that what? So that. This is the golden rule of PDFs. The total area equals 1. Total area equals 1. Right? The total area represents the total probability, and the total probability better be 1. That's what probabilities do. That's why it's got to be 1. In this case, the total area, what is it? It's base times height divided by 2. Base times height. Base times height divided by 2. That equals 1. And then no tricky tricks. Just put in what you know and what you have. The base is B. Does B stand for base? Was B for base?
No, it just happened to be a B.
Okay. The height, 0.2. And then you divide by 2. That equals 1. And then you solve for this however you want. The way I did it, I said B times 0.2 divided by 2 is B times 0.1. So 1/10 of B equals 1. And if 1/10 of B is 1, then B equals 10. Very nice. Way to do it. I guess you could say, you could add a step, B equals 1 divided by 0.1 and simplify it. I don't know. However you do algebra. Okay, so now we know B. Questions or comments about B? I think B was a little bit easier than the rest of it. But now let's do the other part, which is to find the area of this triangle. The area of this triangle. So the probability x is bigger than 1 equals the area of that shaded triangle. Area of shaded triangle. And again, you can do all sorts of tricky things. So you can use like proportionality. This is 1/10 of the way to B because B equals 10. And then you can do some tricks with proportionality. But let's pretend we're just doing it the simple way. This is a line. What is the slope of this line? Slope equals rise over run. And we just figured out the rise and the run. The rise is 0.2. The run is 10. So this is a line of slope 0.2 over 10, also known as 0.02. So the slope of the line is 0.02. You move over by 1. What is the height over here? The rise of this is the slope times the run. And the slope we said is 0.02. And the run is 1. So the height of this point is 0.02. 0.02. Okay, and now that I've said it, it actually looks obvious. It's 1/10 the height of the full thing, right? You're 1/10 of the way on the x-axis, so you're going to get 1/10 of the height. Makes perfect sense. But now we can just be very simple people. The area of a triangle is base times height over 2. Base times height over 2. The base is 1. The height is 0.02. And we divide by 2, also known as 0.01. Oh no! 0.01. I said the answer was 0.99. What's going on? I made a mistake somewhere. Yes.
That would be the probability that x is less than 1.
Yeah, that's right. I did the probability of x bigger than 1 I said is the area of the shaded triangle. This equal sign is not right. That I actually did the probability that x is less than 1. Let's find a pen that works. Well, let's see. Here's a green one. So the area of the shaded triangle is the probability that x is less than 1. That's what I did. This little shaded thing. And that's because, look, it's the area between x equals 0 and x equals 1. That's this. Anything that's in between these two things, that's the area we're talking about in the PDF rule. So that's probability x is less than 1. And now I find out what I actually want by doing a reverse root. X greater than 1 is 1 minus the probability x is less than 1, also known as 1 minus 0.01, is 99%. Okay. That's the area of everything else. That's all this area. But I didn't know the formula for the area of a trapezoid, so I used 1 minus the area of a triangle. Okay. Questions or comments? Yeah.
How did you get the rise?
How did I get the rise? Over here
No,
or over here?
over there.
The second one.
Yeah.
The second one. So I was trying to figure out how tall is this little triangle. So I was doing this little shaded triangle. I said, how tall is that little triangle? And I said, this little triangle is the rise of this line when you run over by 1. So I used the formula rise equals slope times run. The slope I calculated over here. The slope was 0.02. And the run was 1 because it's 1 over. So it's kind of the reverse. Over there, I used the rise and the run to calculate the slope. Over here, I used the slope and the run to calculate the rise, but of the little triangle, not of the big triangle. You can skip all this if you just want to think of similar triangles. This is sort of the hands-on way to do similar triangles.
Yeah, so congruent triangle simply says that, you know, if this is 10 long and 0.2 high, and then this is only 1 high,
Yeah.
and he says triangle is congruent with that bigger triangle, so this height has to only be 1/10 of that height, so that's where you can get 0.02. So that's 1, that's
Right.
0.02, and half of that, when you multiply those two together, gives you 0.01. You got that area of that little triangle, and subtract that from 1, and you've solved your question. And you're very happy at that point. When you say you're very happy at that point,
I'm 99% sure you're quite happy to be done the problem.
okay. So I want to show you one other here. We'll leave this for you to look at before next day. Well, we got a couple more we want to give you before next day, but we'll get this one in. So one of the things is, so far we've shown you the PDFs, Mihai,
Yes.
we had another triangle question that was almost like our first one.
Oh, right.
Set
The
as a
really narrow.
magnetize. Yes, let's do that, because that illustrates an important point.
Yeah.
So let's get to this important point
So
right now.
let's do this.
So this one we're not giving you very long. We've got, because we only got like 2 minutes, so you get like 1 minute to solve it.
So here, in this one, it's the same kind of opening problem. In our opening problem, it was from -2 to 2. This problem is going to go from, let's say, -1/3 to +1/3. And if you go and you calculate how tall this triangle needs to be to make the area, what does f of 0 have to be to make this triangle have area 1? What should f of 0 be? You will find a very surprising answer, which is that f of 0 equals 3. And this gets me quite puzzled, because probabilities are supposed to be less than 1. And yet I got f of 0 equals 3, which leads to an interesting philosophical conundrum over here that we must resolve. And that is, here in the Mathematize, can you have the value which is greater than 1? True or false? It is possible for a probability density function f to take on a value which is greater than 1. And we'll have you guys put in your answers, and maybe we'll do a dramatic reveal exactly at 4:20, which is when dramatic things happen. And then we'll take up the answer next time. Probably there's like 40 seconds left till 4:20 here. So let's see what you guys think. Can the probability density function take on a value like 3, which is greater than 1?
so glad to get this one in.
Yeah, this is a good one. Yeah.
Another level of broad.
All right, everybody. It's exactly 420, and exactly 69 people have answered. So we have reached 420.69, and the answer is 51 people said true, 18 people said false, and you guys got it right. So a probability density can be bigger than 1. We'll talk about it next class. Common misconception.